and welcome to your waves review. Okay, there are a lot of questions about waves, so please make sure that you pay attention and rewatch anything or ask questions about anything that you don't understand. Okay, so for this first standard, there are 4 questions about this, okay? And the big thing here is that wavelength and frequency are inverse. Remember, we've talked about that's our fancy math word to mean opposite. When one goes up, the other goes down. So when your wavelength, your distance between the waves is really small, then you're going to have a really high frequency. If you wanted to count the frequency of this particular wave, you would go 1, 2, 3, and you would count all the way across. This one would obviously be higher than this one down here. Remember, when you have a higher frequency, you have more energy, okay? Because the wave is transferring energy more frequently, okay? High frequency. In the second example, your wavelength is bigger, the space between the waves is larger, it's a larger distance, which means that the wave is less frequent, the space between, the crests come by less frequently. And so that wave is going to be carrying less energy. Right? And that's what we just talked about, longer wavelength, lower frequency, shorter wavelength, higher frequency. Higher frequency means higher energy. Alright, when you're looking at the electromagnetic spectrum, this shows you the wavelengths of different types of light. And so the type of light that's going to have the lowest frequency is going to be radio waves, which means radio waves have the least amount of energy. And the type of light or radiation with the highest frequency would be gamma, which means that gamma waves would have the most amount of energy. Alright, let's talk about sound. And we know that sound is a compression wave, and in these pictures, it looks transverse. A lot of times we draw sound this way because it's just easier to see or easier to deal with. If you want to change the loudness of a sound, then you're going to change the amplitude, which is the height of the wave. So if you were illustrating sound that was really quiet, the distance from the resting position to the top or the resting position to the bottom would be very small. That wave would have a very small amplitude to denote that it is very quiet sound. Okay? If you wanted to draw a wave that was loud, then you would need to draw a wave with a big amplitude, which means it is really tall. Okay? So tall waves are loud. If you were talking about the pitch of the wave, then what you want to change is the frequency. So a low pitch would have a low frequency. It would have a long wavelength. The waves would be really far apart. If you want to draw something with a high pitch, then it would need a short wavelength and a high frequency. Okay? Please remember that louder and higher are not the same thing. Higher has to do with frequency. Pitch has to do with frequency, whereas loudness has to do with amplitude. Remember that amplitude is measured in decibels, whereas frequency is measured in hertz. Okay, next topic, there are 4 questions about this, the difference between electromagnetic and mechanical waves. Remember that electromagnetic waves do not need a medium in order to transfer energy. They can travel through a medium, they can also travel through a vacuum, like outer space. Okay, examples of electromagnetic waves would be light waves and heat waves, and we know that electromagnetic waves travel really, 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 really fast, much, much faster than a mechanical wave. Okay, and all electromagnetic waves are going to be transverse, okay, which is going to be up and down. Your mechanical waves, those are waves that have to have a medium. They have to have substance. They have to have matter in order to travel because they're actually moving through the particles. Okay, so examples of mechanical waves, the biggest one we've talked about would definitely be sound. We've talked about how there's no sound in outer space because there's no particles for the wave to travel through. Also, earthquake waves, which can also be called seismic waves, water waves, all of those things are mechanical waves. Okay, waves can travel in 2 ways. They can be transverse, which means that they're going to travel perpendicular or up and down to the way that the wave is moving. So the wave is always going to move this way, but the particles are going to go up and down. down as the wave goes through them. There's also waves that go longitudinal, or they can also be called compressional, and that is where the wave moves forward, but the particles move side to side. Okay, so sound is the biggest example of this. Alright, and this is just reminding you that light travels much faster than sound does. Electromagnetic waves travel much faster than sound does. That's why we see lightning before we hear it. Remember, thunder is just the sound that the lightning makes. Or sometimes when you go outside and you hear a plane, you look for it over there, but it's actually already over there because the sound is traveling so much slower through the air than the light is. Alright, we've already talked about this, but it's really important, so I'm saying it again. Longitudinal or compressional waves have to have a medium in order to travel. They cannot travel through outer space. If you change the amplitude of a sound wave, you're changing the volume. And if you change the wavelength or the frequency, then you are changing the pitch. Alright, 3 questions about this topic, and these are wave behaviors: reflection, refraction, diffraction, and interference. So reflection is when waves bounce. Light can bounce, so can sound. When sound bounces, we call that an echo. When it hits the barrier and bounces back. Okay? We can use the bouncing of sound in lots of different ways. One of those is sonar, where they know the speed of sound through the water, and they can tell when they measure how long it takes to bounce back, then they can tell how far it traveled or how deep the ocean is. Okay? The next type of wave behavior is refraction. Refraction is when a wave bends because it changes speed, because it goes through a different medium. And so the biggest thing we talk about with this is light. We're going to talk about how when light goes from air into water or air into glass, it slows down. And when it slows down, it's going to cause it to bend. Okay? So anytime the medium changes, you're going to experience or see some refraction. Remember that light travels faster through a gas, slower through a liquid, and the slowest through a solid. If the matter or the medium is really dense, meaning that the particles are really close together, then that is going to slow light down. Okay? When you're talking about the angles of refraction, whenever light slows down, the angle is always going to bend away. So it's going to bend down, like in this first example. If light speeds up, then it's going to actually bend up. So if it was straight, it would be here, but because it's going from glass to air, it's going to speed up, it's going to actually bend up. Alright, diffraction also has the word bend in it, and that's where people get confused. The diffraction is not bending because you're changing the substance and changing the speed. It's bending because it's going around something. It could be going through a smaller opening or around a corner. Okay? There's also interference, which I don't have a slide for, and that is when sound waves actually interact with each other. If they interact with each other and they make a bigger wave, then that is called constructive interference. So a sound that happens a lot when things get louder. Okay? If they interact with each other and they cancel out, then that is called destructive interference, and that is how noise canceling headphones work. And that is going to make the sound quieter. So there's constructive interference, where they come together and they make a giant wave, and there's destructive interference where they come together and they cancel out. They destroy each other. Alright, the Doppler effect. Don't think that's on the funnel, but just in case, the Doppler effect has to do with when you have something that is moving, the sound waves are going to get squished in front of the object, which is going to push them together and shorten their wavelength, which we know is going to increase their frequency, and so it's going to sound like a high sound. And then as the object goes by, the sound waves will spread out, which is going to lower their frequency and lower their pitch to make it have a low sound. So when something goes by, it sounds like meow, even though we know in reality, if we were moving with the object, then it was one constant tone. So the Doppler effect is just caused by a moving object. Okay, so 3 questions about this next topic. So again, remember that sound has to have a medium. So if there's no matter, there's no sound. Okay? Sound is going to travel the fastest in a solid, and that's because sound is a mechanical wave, which means it's moving through matter, moving through materials, and in a solid, particles are really, really close together. And in class, we set up dominoes. We saw that in a solid, when the particles are close together, then the wave traveled really fast. Whereas in a gas, where the particles are farther apart, then it's going to fall over a little slower. If two materials are the same substance and one is hotter, then sound is going to move faster because the particles themselves are moving faster. But you only need to worry about temperature if you have two exact substances, like 2 cups of water. One's 100 degrees, one's 50 degrees. Sound will travel faster through the 100-degree cup of water than it would through the 50-degree one. Alright, so if you look at this data table, you can see that density, which again, density is just how close together things are. When things have a higher density, meaning that they're closer, then you can see that sound is going to travel a lot faster. Solids are more dense, which is why sound travels faster through a solid. Light is just the opposite. I told you to think about light like traffic. So when there's a lot of particles in its way, it's going to slow way down. So if we look at this slide, we can see that light is going to travel the fastest in a vacuum, like outer space, because there's barely anything in its way. And then next it would travel through air, and then water, and then different solids would have different speeds. In this particular example, diamonds would be the slowest, because the particles are really close together and get in the light or electromagnetic waves way. Alright, if you look at this particular example, then we know that that blue light would have the most energy and would travel the fastest, and then red would have the least amount of energy. Alright, so that is all for waves. Please make sure you study.